There it rains literally glass. Then your question might be, do you have green stars? Yes, we have, but it's a continuous transition. It all depends on the temperature of the star. There exist stars that are still there and that have been created shortly after the Big Bang.
Welcome to the 26th episode of Apple Finch Pudding, your gateway into the world of science. Today's scientist is Leen Decin, a professor in stellar and exoplanet astrophysics at KU Leuven. Her work focuses on stellar evolution and the composition of exoplanets. Welcome, Leen.
Hi, Jeroen.
Before we start, my first question is always more or less the same. Do you have a fun science fact for our listeners?
So you just have introduced my field of expertise, which is at one hand stellar evolution and at the other hand also exoplanets. And maybe something that people don't know is that we have, let's say a few years ago, people have thought and are still thinking that there is one of these exoplanets that has a very particular name, being HD 189733b, and we think actually that it rains glass there sideways, so that it's a kind of a sideways raining of glass particles. So to the human eye, this far-off planet looks bright blue, but any space traveler confusing it with the friendly skies of Earth would be badly mistaken. The weather on this world is deadly. It has very strong winds, up to some 7,000 kilometers an hour, and whipping out all would-be travelers in a sickening spiral really around the planet. But when you would even then get caught in the rain of that planet, it will be more than an inconvenience. It's death by 1,000 cuts. So we have, by looking to the data, we have diagnosed that there are very small silicate particles there, but they are glassy. And so you have this very strong winds with a lot of silicate material, glassy silicate materials. And as such, we hypothesize that exoplanets, that there it rains literally glass. So if you would confuse that planet with our Earth, it will be a very bad travel.
Yeah, it really sounds like a horrible death.
It's like that, so.
Maybe also, how do we know that it's raining glass?
Well, we always build our hypothesis on several pillars. First of all, you need observational data. And then you need to analyze this data not by only looking what we call to the spectrum. So spectral is just something that tells you, it gives you fingerprints, chemical fingerprints. And so you analyze these chemical fingerprints at one hand by looking at this data, but at the other hand, you also do extremely detailed hydrodynamical and chemical simulations. And then you need one of these simulations that is predicting what we see in this data. And so it's based on this data and then also the models that we can tell you something upon chemical composition, wind speeds, temperatures, etc.
Before we dive more into exoplanets, I was actually planning on starting with stellar objects.
You go ahead.
Okay, so starting very broad, what are stars and where do they come from?
Well, stars are celestial bodies. A star is born literally in the interstellar medium. So how does it work? You should compare it with, if you don't clean the house, you don't clean the kitchen or the living room, you see that your dusty particles, they tend to collide. Similar things happen in the universe. In the interstellar medium, you have also that particles tend to collide. And so we have that attraction of the material and they come together. Now, if you have a lot of material together, there will be a collapse, a gravitational collapse of the molecular clouds, as we call it. Now, such a molecular collapse, you really come from a very big object to something that is really small. And in that transition, the temperature goes up a lot. And when the temperature increases above some threshold, you get nuclear reactions that take place. And when their hydrogen is turned into helium, and we call that the nuclear burning, a star is born. So also our sun is one of these stars. It's a very modest star. So it's a quite small star. It's yellow in color. But so we also have big stars that are blue in color, and we have cooler stars that are red in color. whether the small stars, when they are born or red, they live much longer than our sun. And the most heavy objects are blue in color, and they have a very short lifetime, since they need a lot of nuclear burning in order to keep, the transition between nuclear burning and again collapse. So the bigger you are, the shorter your life will be.
So bigger, heavier stars burn faster, actually.
It is.
Okay. And so you mentioned already some types of stars, like blue stars, red stars, yellow stars. How many different types of stars are there?
Well, we have them in all kind of colors, but most of the colors are even not visible to the eye. So I tell it to you as being a color. It's literally color. You see that, for instance, our sun is yellow in color, but that mainly implies that most of the photons, or the light particles that we get from the sun, are emitted in the wavelength band that is yellow. But what it also implies is that the sun has blue photons with a shorter frequency and red photons with a longer wavelengths. And so that together, it implies that the sun has its peak of the photons in the yellow, and then it has a lower amount of blue photons and red photons. But so we call that the Planck curve. It also implies that the red stars, think upon a flame. When you have a flame, it's hotter in the blue side than in the red side. So hotter implies a blue color. And so then your question might be, do you have green stars? Yes, we have. But it's a continuous transition. It all depends on the temperature of the star.
And is it then also possible to have more or less invisible stars that are burning in the spectrum that we cannot see with the naked eye?
Well, yeah, they are very small. We have also what we call brown dwarfs. These are more or less failed stars. They were too small to really start that nuclear burning at the inside. And yeah, also the smaller the star is, the less probable it is that we will detect it.
So in terms of how you said it before, it's like stars are the coalition or the colliding of dust in space.
Dust and gas.
Dust and gas.
Yeah,
And
yeah.
there's not enough dust and gas for those small stars, so they don't have enough mass to ignite.
Yes, yeah.
And so you mentioned the sun is a yellow star. What does that imply? For example, how long will the sun be there for?
Okay, the sun, the current age of the sun is roughly around 5 billion years, and it's midway of its lifetime. So we expect it to still live for an extra 5 billion years. So roughly 10, all dependent on the models that we are using, between 8 to 10 billion years, the total lifetime will be for our own sun.
Stars undergo a whole evolution. Is there a general evolution, or is it really dependent on the different types of stars as well?
Indeed. So it's yes and yes to both your questions. So we have a feeling, we know how stars in general evolve, but also dependent on the mass, it will be slightly different. So for our own sun, which is currently, as we call it, the main sequence star, later on it will evolve towards a red giant branch star. And red and giant are really the correct words. It will become much larger, it will expand in size, and also become much cooler meanwhile. It will change from the yellow color towards the reddish color. And so it will enlarge so much in size that even currently we do not know whether it will engulf or not our own Earth. Since it's expanding, it's really expanding by a factor 100 or a few hundred in size. And then later on, when the sun has become a red giant branch stars, roughly twice even, it will die as a small white dwarf. And again, dwarf means it will literally become very small. White is it will at first be very hot, extremely hot, above 10,000 Kelvin and even much more. And then slowly it will dim and it will cool down. And this is how our own sun will die.
So, and it starts by expanding, but why does it start expanding?
Well, this has all to do with the nuclear reactions and the nuclear burning that I just explained to you. At some point, at the core, the center of the star, there will not be enough hydrogen anymore to burn. And then we have other cycles of burning that will start happening. And in these transitions, what happens there is that you have convection and radiation, and altogether then we can show indeed that this implies an increase in the size of the star in order for some physical law. So in this, that was hydrostatic equilibrium, but that's still to be valid. So you really see the laws of nature, they apply to stars as well, and we see how these laws imply if a star will become smaller in size or whether it will increase in size.
And yeah, so it increases by 100-fold. Is that the same for all types of stars, or do some stars even get a lot bigger still?
So all it again dependent on the mass. So there will be stars that will become. So our sun will become a giant star. We have stars that will become supergiants. So there will be even a factor 10 or more larger than our own sun when our sun is a giant. So and these are typically for stars that have an initial mass that is larger than our own sun. So our own sun, 1 solar mass. When you go to 8 solar mass stars and above, they will go to the red supergiant phase.
As you said, so the age of a star or how old it can get depends on the size and the mass. But like, for example, if a star dies young, what is young for a star or what is old for a star?
Well, young for a star is even less than 1 billion years. That's young. This is for these very massive stars. Long for a star, well, there exist stars that are still there and that have been created shortly after the Big Bang, so roughly 14 billion years ago. So these are these very small, tiny stars that don't need a lot of fuel to live, and they are still there. They are beloved. They have an initial mass below roughly 0.8 solar mass. So we know that these stars haven't evolved much yet.
That's insane, actually.
Yeah.
And are there still some questions that we really don't know about the evolution of stars?
Many questions. Otherwise, I would not do research, isn't it?
Yeah, that's true. That's true.
I can spoil you with a lot of these questions, but so I have just given you the rough outline of stellar evolution. I just have told you, for instance, that stars at some point will become red giant stars. We also know that during that phase, stars are losing a lot of mass. And so just let's go back to the bigger picture. So what happened shortly after the Big Bang is we have had the first stars are born, and sometime later the first stars are dying. Now, what is happening, as I just have told you, is that some of these stars, come giant stars, supergiant stars, they lose mass. Now, what does it mean they lose mass? It implies that deep inside these stars, I just have told you, you had this nuclear burning cycle. So it's a kind of a nuclear reactor. So they make new chemical elements. These chemical elements are created deep inside the star. By convective patterns, they go up to the surface of the star. And then you have the mass loss rate. The mass is lost, so you get these newly created elements are injected in the interstellar medium. And stars that are born later on, they get these new elements. So for instance, in the beginning, just shortly after the Big Bang, there was almost no carbon, no nitrogen, no oxygen. Our sun has taken quite a long time before it was born, some 9 billion years. In that instance, other stars have been born and have died and have put carbon, nitrogen, oxygen, etc. in the interstellar medium. So at the moment our own sun, was born, there was already carbon, there was already nitrogen, there was already oxygen. And that is the reason that here on Earth we have these crucial building blocks for life. When our sun would have been born much earlier, shortly after the Big Bang, we wouldn't have had so much carbon, nitrogen, and oxygen, so life would not have been possible. And so it's thanks to the life and death of other stars, that we can live here on our own Earth, that life has been possible.
If I understand correctly, all chemical elements are actually the result of dead stars. And
Roughly,
yeah, more
yes.
or less. Maybe that's an interesting question. Which ones aren't?
Well, hydrogen and helium are made in the Big Bang, a little bit of lithium, and all the rest comes from the stars.
Yeah, so all the heavy elements.
Yes, all what we call the heavy elements, indeed.
And what happens, for example, when two stars would collide?
We think that for stars above, let's say 1.52 solar masses, most of them do have at least one companion, but a companion can be a planet or can be a star. The higher the initial mass of the star, the more likely it is it will have a companion. So what is then happening is that these stars, they live together. The evolution of one star can impact the evolution of the other star. And so it might happen, as we were just asking Jeroen, is that these stars collide. If they collide, you have a lot of other phenomena taking place. We see a spike in the energy. You can have the creation of gravitational waves if they are massive enough. So if you have two neutron stars, or if you have two black holes, etc. So you have a lot of new physics that is happening at the moment that two stars collide.
Is it then also possible, because I think it was in Star Wars, that there was a planet that had two stars. Is that physically possible?
And we even have detected some of those planets already. So what might be is that you have two stars, and around either one of these stars, or around both of them together, you have a planet that is circling around. And so then you can have a planet that have two mornings. It all dependent, or two sunrises, let's call it like that. All dependent on the position of the two stars with respect to the planet.
The planet is then circling around the two stars, or can it be circling, for example, more or less in a figure eight or something? Or what are the possibilities?
There are many possibilities, all dependent on the stability of the system. So I can give many examples. The planets that has been detected are thought to be circling around one of these stars, but there are many possibilities. And when it comes into dynamics, you can have many solutions.
What are some of the solutions that you have detected?
In terms of binary stars or in general?
Can do both if you want.
So what we recently have been discussing quite in detail in the literature is that, well, let's go back to the sun, and the sun will become a red giant star. And so for a long time, it was thought that most of these lower mass stars, they don't have companions. But what we have seen in our data is that when you're looking to the signatures of these stellar winds, we do see specific patterns. We see that there are in the stellar winds of evolved stars, of these giant stars, we see spiral-like structures, we see kind of disc-like structures, we see many things, many morphologies. And the only way to explain these morphologies is by hypothesizing that these winds are shaped by companions, so that these are not single stars, but they have a stellar or a planetary companion that is circling around them. And while the old star is losing mass, the other one goes around it and is really shaping the signature of that mass. And so this is something that we have clearly seen in our data 2-3 years ago, and that is now really changing the field, since it implies that some of the diagnostics that we have been deriving to understand stellar evolution, for instance, the strength of that Maxwell's rate, are just wrong. And so we really have to rethink and remodel a lot of the stars that we know of.
And stars at the end of their life, they can become supernovas. It can also turn into black holes. Is that the difference between mass again, or is there something else at play here why they have so different lifetimes?
Well, for stars that are more massive than roughly 8 solar masses, they go to the supernova phase. And then all dependent on the particular conditions, they will either become a black hole or a neutron star. And I say particular conditions, this all implies when how much mass has it lost, etc., etc. There are some details we don't understand yet. For instance, the interaction with its companion, since we know it will have a companion. And so all dependent on the particular environment and particular mass it still has, we have a black hole or a neutron star.
What is like one of the major breakthroughs that you foresee for this type of research for stellar evolution?
In the near future, it will be well, it might sound boring, but it will be the understanding of really that binary interaction. How does it work, and how much, for instance, mass of one star can be accreted by the other star. And so we need to understand that physics and that chemistry properly if we want to do decent predictions in terms of gravitational wave events, if we want to say something upon supernova explosions, etc.
Doesn't sound boring to me at all, actually.
Thanks.
So if I understand, you want to know how much of also heavier elements in one star can actually come from another star. Is that correct?
That's a broad view of stellar evolution. Indeed, you need to understand what individual stars are doing to extrapolate that then for your full population and tell you something upon the big picture. It's a bit, you can also compare it a bit as with a fruit fly, Jeroen. If a fruit fly flies over the market for one day, the fly has a kind of a view on the fact that people are born and then they die, and you have some sampling of your population. This is also what we do. And we have the current stage, we see stars at different evolution. And by looking at that, we can give you the general picture on what are stars doing. So I don't need to understand all stars. I need to understand the sample of them. And then I can tell you something upon stellar evolution.
Imagine that we have solved this puzzle and you know how much of heavy elements in one star is coming from another star. What will that tell you?
Well, one of the big questions we are still after is understanding, let's say, the evolution of the table of Mendeleev. We all have seen the table of Mendeleev when we were at secondary school. And so, but we see there, as I just have told you, that the chemical evolution is changing from element to element. And we would like to have a better understanding on how that happens. So that's really delving deep into some fundamental understanding of our universe.
Is it then also looking into why we have different isotopes of different chemical compositions? Maybe just in general to know, so like isotopes, that's, for example, you have carbon-12, carbon-13, carbon-14, so it's the same element, but they have a different type of neutrons. Is that also what you're looking into?
For instance, we use not carbon, but we use the oxygen isotopes to really tell you something on the age of some stars. Since in these nuclear burning cycles, some of the isotopes are preferred more than the other. And so by looking then to the ratio of these oxygen isotopes, we can really, let's say, age date our stars. That's one of the ways how we use these isotopes to tell you something on the life of on the age of a particular star. And also we can use that to determine the mass of the star, for instance. That's also another way of using these isotopes.
Do you know, or is there a simple way to explain why, for example, we have carbon-12 most of the time and not carbon-13, or oxygen-16 and not oxygen-18?
That's going back to the same thing. It's this nuclear burning. In this nuclear burning, you have not one reaction that goes to the other reaction. You have several reactions that can take place, all dependent on the particular conditions inside the star. And so you have not only the nuclear burning, but then you need also these convective patterns that bring these elements created deep inside the star towards the surface. And so all dependent on the mass and on the efficiency of each of these processes, you have as a consequence that some of these isotopes are more preferred than other ones.
I just think it's so interesting because we have these different isotopes, and when we study it, they just tell us there are isotopes, but we never get told why there are different isotopes. And that's so interesting that you're actually looking into this and how this works. So now we have our heavy elements. Those can be used actually to form exoplanets. How do we look for exoplanets? Do you use the transit method? And maybe also explain the method if you can.
There are various methods to detect planets. So you mentioned one that is most frequently used, but let's say the first detections were not a transit method. So what if you can see my hands also, if you have two planets around a star, the planet goes around the star. But there is gravitational attraction. That's also the laws of Kepler. The laws of Kepler tell you indeed the planet goes around the star with the planet in one of the focal points, with the star in one of the focal points. But what is also happening is that small planet is really interacting with the gravity, does have a gravitational interaction with the star. So while the planet is going around, the star is also moving, like this. You see this happening. So the first planets that have been detected were not detected since we did see the planet, but since we did see the mother star turning around. And when a star is turning around, you have, if the light comes towards you, it's blue shifted. If it goes away, it's red shifted. You remember potentially the Doppler effect? We have the similar thing here. So what we did see is that when we were looking to the spectra of these stars, we did see the spectral features continuously changing in a very irregular way. And this was just, the cause of that was the fact that that star was turning around the common center of mass. And this is how the first planets have been detected. The first exoplanet around a solar type star was detected in 1995 with that kind of technique. Now, you were also mentioning now the transit method. The transit method is a specific method that only can be used if the planet is really transiting. It means that it passes your line of sight. So when you then have the star and then you have this little planet that comes around, it dims a little bit the light of the star. And it's a really extremely small fraction. I'm talking upon 1 out of a million that it dims the light. So when the planet transits, you see slightly less photons from the star than when it goes away. And so what you continuously see is you see a very small dimming in the light, and then that dimming comes back. That's the transit method. And then all dependent, so you can look at the transit method at a particular frequency. Let's do it simple. You look in it in the blue, and you look at it in the red, and you will see that the dimming is slightly different in the red channel than in the blue channel. And all dependent on that difference, I can tell you something upon the chemical composition, upon the fluffiness of the planets, of its atmosphere, etc. So we can use the transit method at different wavelengths, and so we combine information of different wavelengths, and that tells you something on the atmosphere of the exoplanet.
That wobbling, I assume that also depends on the mass of the star and the mass of the planet. If there's a really small planet and a really big star, I don't think that will have a big effect.
So for instance, our Earth, it does imply our Earth causes an extremely small wobbling of our own sun. When we would look at our own sun from another planet, we would mainly see the wobbling caused by Jupiter and not by our own Earth. So the more massive the planet will be, the more pronounced that wobbling around the common center of mass will be.
And you also already mentioned it, that's actually that we might have gotten wrong in the past. So is it right that every star can have exoplanets, or at least something swirling around it?
Yeah. We now think that for sure, not for sure, but let's say most of the stars above 1.5 solar masses will have at least one planet. We think so. In general, we think that that's a rough answer there. There will always be a planet with a star without a planet, and that can also happen. We also have lonely planets that were formed out of the debris disk and were kicked out. That also happens. But that's the rough answer there. Most of the stars do have a planet.
Combining what we've talked about, we have different types of stars. Can every type of star have exoplanets, or is there also some limit to that?
We don't know yet. We are currently building up what we call the population statistics. It seems again that the higher the mass of the star, the more likely it will be that it will have a planet. But yeah, we currently have a detection of, let's say, some 5,000, 6,000 exoplanets. but there is quite a bit of a bias in this detection. Bigger planets are detected more easily than smaller planets. If a planet is more closer to its host star, it will also be detected more easily. And so we correct for these biases, but even then there are quite some uncertainties in our answers. And so currently it's not yet, I would not say that there is any firm answer to your question. There will be dependence on mass, there will be dependence on the chemical composition, where the molecular cloud, the chemical composition of the molecular cloud, but we're still, we are still building up our knowledge there.
Based on these methods that you mentioned, what can we know about exoplanets? So you already told us we can have some idea of the chemical composition and the fluffiness. Is there something else we can know as well?
Well, we know quite a bit already on the dynamics, on the temperature, the wind speeds, the chemical compositions, in particular for planets that go into transit. This is something that we can start studying in detail as of a few years, and in particular now with the launch of the James Webb Space Telescope, roughly 2 years, well, 1.5 years ago, or even longer, no, 1.5 years ago. So this is what we can start looking at. What we also do is from this population statistics that we have on planets is trying to build up our understanding on how do planets actually form and how do they evolve. Are some of these planets, for instance, I was just telling you something on these evolved stars in the beginning of the podcast. Well, detecting planets around these giant stars is extremely challenging. We even didn't know how to detect them. But what we now have done, let's say a few years ago, is we have started detecting planets not around these giant planets, but around the next stage, the white dwarfs. So we know that planets can survive the giant phase, are not kicked out. Part of them, some of them will be engulfed by the host star, but not all of them. So just by looking then to the next stage, we can infer something on the formation evolution of planets in the former stages.
We have been talking about heavy elements and exoplanets, and it actually brings me to one of your papers, and I think it also touches up on the fun fact you mentioned earlier. So the title of the paper is SO2 silicate clouds, but no CH4 detected in warm Neptune. That's a paper you co-authored, and maybe start with the beginning. What are warm Neptunes?
A warm Neptune, well, it's a pen. So WASP 7b is a planet with the size of a Neptune, but with the mass of a Neptune, but the size of Jupiter. It's much larger than a Neptune. Warm is, for us, warm is a temperature around, let's say, 500 degrees Celsius. I will say it in Celsius now, that's easier to understand. So you have cooler planets, you have hotter planets. Warm is, it's roughly defined, let's say around 500 degrees Celsius. So that's a rough outline of WASP 7b. So as Neptune, but much larger in size. So the atmosphere is very fluffy, not dense at all. And its temperature in this atmosphere is around this 500 degrees Celsius.
So basically you say you found silicate and not methane. Methane is also a common greenhouse gas on Earth. So how does that happen?
Well, it's a good question. We were expecting, so with James Webb, we were expecting to see methane quite prominently in quite a lot of data. And much to our surprise, we don't detect it. So we now try to understand why not detecting it. One of the possible hypotheses there is that these planets are much hotter even at the inside than what we were detecting, or what we were thinking. I was saying you that you have a temperature around 500 degrees Celsius in the atmosphere, but when you go towards the interior of the planet, the temperature increases. What might happen is that the temperature at the interior is higher. If we indeed do simulations with higher interior temperatures, we don't get methane. This has all to do with chemical reactions and chemical equilibrium or disequilibrium. So that's one of the hypotheses. It might also be, and then we jump already to the other point that you are making, is that there is methane, but that we don't see it since it's hidden by a cloud. We have seen in this data that there are clouds in the atmosphere of the planet. before we went into this study, we did knew already that there were clouds, but we could not tell you anything on the chemical composition of the clouds. What you can see is when a planet has clouds, I was telling you in the beginning that we see these spectral fingerprints. When you have clouds, it is as if these fingerprints are cut. So what we did see in the data is in previous data, we did see very weak fingerprints of, for instance, water vapor. So there was already an indication of clouds, but we could not tell you anything on the chemical composition of the clouds. Now with the James Webb data, we have looked at other wavelengths, and these other wavelengths allowed us to determine the chemical composition of the clouds. And these seems to be, according to our analysis, silicate clouds. So they are not made of water vapor as the clouds here on Earth, but they are made of small, but we think more amorphous, not glassy, but amorphous silicate particles, a bit as sand here, the sand particles here on Earth.
So I assume, because you say it's so warm there, or we assume it's not possible to have life there?
No, it cannot. It is a gaseous planet, so we cannot live there, not at all. The temperature of this 500 degrees Celsius wouldn't fit us either. So it's not possible to have life as we know it, to have it there.
And is it common in your kind of research to compare exoplanets to planets we know from our solar system?
Yeah, since that's the main benchmark that we have. For the planets in our own solar system, we have much more data available than what we have for these exoplanets. So it would be weird not to compare to our knowledge and to our data that we have here on the solar system planets.
Yeah, of course. But I assume you might also find planets that have nothing or close to nothing in common with the planets in our solar system.
Yeah, true. Our own solar system is only one benchmark. And so that's a very limited viewpoints. So by looking to these exoplanets, we detect a zoo of exoplanets that don't have any resemblance to what we know here from our own solar system planets.
And what are some of the weirdest planets that have been discovered? You already mentioned a planet where it's raining glass. Are there some other special ones?
Oh, you have, well, this was Pano 7b. It's very fluffy. It's a very thin atmosphere. We think we have detected planets where there's a lot of carbon available. So we have more carbon than oxygen. Well, most of the planets have more oxygen than carbon. And then, we have planets that are potentially, and then that's always exciting, in the habitable zone of their star. But we don't know for sure. We don't know whether there's life. Habitable does not mean habited. That's still something different. So we have a lot of things that we can wonder about.
And is it also part of your research looking at the possibility of life on exoplanets?
That's always the question that you get. But we only, let's say, discuss it as an astronomer. You discuss it in terms of habitable, what we just were saying, if the temperatures might be potentially right for life to form. Also in particular, when you think that there might be liquid water, which is very important as a catalyst for a lot of chemical reactions that can lead to life-forming processes. So that is, let's say, the very limited astronomer's perspective. For sure, these data are taken and also sometimes to the next step by people more into chemistry and biologists. But that's with a lot of uncertainties, since our knowledge is it's very much centered on what we know here on Earth. So to broaden up that perspective, to understand chemical reactions that you have never seen here on Earth is challenging. And so we try to do that that's a lot of chemical, let's say quantum chemical work that we are doing, a lot of theoretical work, trying to extrapolate, to understand how chemical reactions occur in these extreme environments, but you also understand that there are a lot of uncertainties involved there.
We basically have a sample size of one, which is Earth.
Yes. And out of that, we extrapolate a lot.
And people that are looking for life on exoplanets, what are they looking for then?
Well, we don't look for, well, looking for life on exoplanets is a dangerous thing here. We look
Or looking for the possibility of life.
looking for the possibility of life is what we then are doing is based on what we know in the thermodynamics, put that into a model and see whether it can proceed towards some life-forming processes. But we even don't understand how life has formed here on Earth, let alone that we would think we have a clever answer on how life can form on exoplanets.
There are a lot of exoplanets, and we assume that there is life on other planets, but if there is, why haven't they contacted us yet?
What is important there is that you have there that very, let's say, call it a deterministic view on the fact that life is intelligence, or that other life can be intelligent, dependent on the definition that we have made ourselves, and that these other creations would be interested even in exploring the universe and in having technologies that can explore the universe. And so there are many steps going from life towards exploration of the universe. And so what I think is it's a bit very chauvinistic to think along those ways, since, well, isn't it a sign of chauvinism to have, let's say, defined, and we did it ourselves, a kind of an imaginary ladder of progression, culminating in something that we call Homo Sapiens, which are much praised intelligence. We are really branding ourselves as being the smartest of the universe, but try not to define, for instance, an evolutionary ladder based on other criteria. For instance, can you fly without external aids? And how good are you in doing that? When we would have that definition, we would not be at the top of that imaginary ladder. But so we are very good in branding ourselves, and we are the most intelligent people of the most intelligent creations of the universe, etc. So isn't that very chauvinistic? And maybe we should, we can discuss these things. Should we do it based on intelligence? Should we use other criteria? So then the question is, what makes us unique as Homo sapiens? Are we really intelligent, that sapiens are not? I think we should go, well, we should maybe if we want to be unique as Homo sapiens, we maybe should rephrase ourselves a bit and say that we are Homo Sentience. That what makes us unique is consciousness, is wonder, is curiosity, is trying to understand the universe. Since it's wonder that is the beginning of wisdom. And then potentially we can call ourselves sapiens, but link then to what I was saying, sentience, and not only towards that pure, let's say, intelligence criteria that most of the people are using.
Okay, wow, that's amazing. Okay, so you study astrophysics, but why do you study astrophysics? Is it important for the general population?
Wherever I go, and when I tell that I'm studying or that I'm doing astrophysics, people are always interested. I have been in Africa, I have been in South America. 2 years ago, for instance, we went to Peru. And when the kids were realizing that I was doing astrophysics and my husband is an engineer, they were not interested in the fact that he was an engineer, but they were interested in astrophysics. And so they asked me to explain a bit on stars and stellar evolution. And I tried also to do that in a way that I did not touch their view on the universe. But you can always, what is the conclusion for me on that is that people need more than bread and butter. People want to know what is the place of humanity in the universe. Independent on where you come from, independent on how you have been educated. And so this is for me a very important answer on why do we do astrophysics, since I want to understand what is our place in this very big, in that immense universe.
And how did you get interested in this topic?
That's mere coincidence, in the sense that I did my education here at the KU Leuven. And so the people that have educated me were working in the field of stellar evolution, not yet planets. And so that is, education is important at that stage. And so throughout the years, then I decided as the first person here in KU Leuven to also start working on these exoplanets. And now we have a bigger team working on exoplanets, but as a team within the KU Leuven, the Institute of Astrophysics, we have decided to have that focus on stellar evolution and exoplanets. So in the past, it was only stellar evolution, now it's stellar evolution and exoplanets. We do not, for instance, go into galaxy formation. We have decided to have that very strong expertise, and that makes us unique in the world. So we attract the best scientists just from the fact that we are really focused, and we can, we have a lot of people working on similar topics, so we can share knowledge. And so this is why we proceed much faster than anybody else in the world on these topics, since we have that critical mass here in Leuven to work on these topics.
It sounds like a very smart decision, actually.
I think so.
Before we close, do you have a take-home message for our listeners?
Use your curiosity to understand the universe.
This was the 26th episode of Apple Finch Pudding. I want to thank Leen Decin for the information. Let's meet again for the next episode of Apple Finch Pudding.